Okay, this time I'm gonna talk about the first midterm about the nanoelectronics and summarize the total thing about the first midterm. I'm gonna study about the SDE, short channel effect. It means punch through or Kidder or Dibble and mobility degradation and velocity saturation. And then we're gonna fix this problem. We used several techniques to the semiconductor. First is we use the strain engineering. Strain engineering is to solve about the velocity saturation. We can improve the mobility through the strain engineering. Okay, and then what is the strain engineering? We can use the difference about the lattice between the other metals. We can select the matter and we can use that matter the different lattice of that matter. So we can recurse about the source and drain. It means the local strain engineering. The source and drain matter is bigger than channel. We can make a compressive strain to the channel and more smaller, it can give the tensile stress in the channel. So we can make it our mobility can control it. So that control improve the mobility and you can fix the velocity saturation. And then the transistor has been used polygate about this time, but we don't use the polygate because there has some problem about that. First is the biggest problem is the polygate make a depression region in the polygate. So it can make another parasite cap and it can be reduced about total cap. So total cap reducing is mean gate coupling down, and it makes a lot of leakage current and it can make reduce the drain current. So we solve this problem. We can take the method about the change the metal. So we can change the polygate and to the metal gate. And then we can use the metal gate and we can use the high K metal, high K dielectric, because the high K dielectric in the is occurred by the thickness of the oxide is too thin and it can make a direct tunneling and it can make a leakage pass. So drain current is so low and power consumption is very high. So we can solve this problem. We can use the high K metal. High K metal is a same thickness and much more coupling is better. So we use the metal gate and high K dielectric to the gate. First is the most ideal high K metal is hafnium dioxide and zirconium dioxide. But there have several problems about the high K metal, so we can use the buffer layer about the silicon dioxide to make it much more energy band offset, so it can prevent the thermal energy gives the electron through the gate. Problem has been denied. And then we can use the silicon to the metal or something other metal. We can make an interface problem because because the reason is the why we can use the other difference matter. It means hetero. So there has a several state and trap. We can call trap. It happened. So we should have to reduce this because this is the called the CIT, 그 interface capacitance. It make a swing. It make it lower poor swing, and it means the not ideal switching operation. So we use this problem. The metal gate, we can several component to the one metal gate. It means a work function metal gate. We can binding the several different metal. It metal property about the work function is different, and we can mix it together. We can control the metal gate to work function, and then we can control the threshold voltage. And then we can control the threshold voltage. We can make it device at the purpose. And then about the gate control, we should have to get a much more gate control. So we use the multi-gate like a FinFET or GAA. Like a GAA is a all surface of the full surface is covered by the gate, and it means a full gate channel. And FinFET is like a SI body, and it is covered by the three surface of the gate. So it can mean a three gate device. So this is the good for gate controlling, and this is the much more ideal device. So there is the manufacture about the FinFET fabrication. There is a oxide growth, and we can use the self-aligned technique and RMG technique, replace metal gate technique. We can make a dummy gate, and we can reduce the dummy gate and filling to the metal gate about what we wanted. So this is the normal FinFET fabrication technique. And then this is the final midterm about this. Thank you.